Rationalizing denominators. And again, to rationalize a denominator, the trick here, the trick here is to multiply numerator and denominator by the same radical quantity in the denominator, that is the square root of 5 times the square root of 5. All right, now when we multiply these two numbers across, what is we get 1 times the square root of 5, which equals the square root of 5. And then in the denominator, what do we have? The square root of 5 times itself, so that's going to be the square root of a product, 5 times 5, which equals to the square root of 5 divided by the square root of 25. And in this case, well, the square root of 5 divided by the square root of 25, which is 5. And we're done. So again, the idea is to rewrite that given quantity with a radical in the denominator in a way that no radicals appear in the denominator. And well, that's and again, the trick is to multiply numerator and denominator to make the denominator a radical of a product of a perfect square. So when you take the square root of that perfect square, see how there's really no radical in the denominator. All right. Another way to visualize this, check this out. Let me focus on the product of these two. Okay, so the square root of 5 times itself. Again, if we go back and write these radicals in rational exponent form, that is 5 to the 1/2 times itself 5 to the 1/2. If we were to combine these two together, well, what do we do with powers, with exponents when we are multiplying the same basis? Add the exponents, right? So we add the exponents, that is 5 raised to the 1/2 plus another half, which in this case is 5 to the first power, which is simply 5. Doesn't that look like the same denominator here in the final answer? And again, by multiplying by the same radical, we get that done. To get rid of the radical notation, get rid of the radicals in the denominator, no matter if we still keep those radicals in the numerator. Again, that's what we mean by rationalizing the denominator. And of course, it works with variables along with, like the square root of y. Simply multiply numerator and denominator by the square root of y and divide by the square root of y. And again, multiplying across, that'll be 1 times the root of y, that's simply root of y, and that'll be the square root of y squared. In the numerator, just root of y is simply root of y. However, the square root of y squared in the denominator, what's that? Just y. Do you see how we no longer have radicals in the denominator? And again, we're still taking advantage of all these properties of radicals we did in the previous radical review handout, and the same cancellation properties between the square and the radical. All right, now be careful with something like letter C. And I know that hopefully by now you have seen the pattern, like just multiply numerator and denominator by the radical that you see in the denominator. However, check this out. Let me do it. You don't have to write this part. Let me show you what you don't want to do. So, which is precisely this. There's nothing wrong with doing this because, again, that's the technique. That's the process we do. However, do you want to do 28 times 28 and get a big number? That might be a little complicated. So instead, how about we simplify this radical 28x? In fact, again, that's going to take us back to what we did last time. Break up the number 28 as a couple of factors in a way that one is a perfect square. All right? Is it the case for the number 28? 4 times 7. All right? Break this up as 4 times 7. That'll give us the square root of 4 times 7x in the denominator, everything in the denominator of 7. Alright, so now we can even go ahead and evaluate the square root of 4. Outside, that's going to go to 2. So that'll be 7 over 2, square root of 7x. Alright? And well, notice the radical in the denominator. I think this one is in its simplest form, so we can go ahead and multiply numerator and denominator. But in this case, only by the radical, not by 2 as well, just by the radical. That is the square root of 7x divided by the square root of 7x. And multiplying across, that's going to give us 7 times the square root of 7x divided by 2 times the square root of 7x squared, that is, well, 7x, let me do 7x times itself, 7x, and then we will simplify this to lowest terms. That'll be 7 root of 7x, and that's 2 times the square root of 7 times 7, that's 49. X times x equals to x squared. And notice how, after doing this process of rationalizing the denominator, notice a pattern. We always end up with a perfect square. We end up with a perfect square. We ended up with a perfect square in here as well, right? That's what you want to get, to simplify the square root of that perfect square in a way that the denominator doesn't have any radicals in the end. All right, so let's keep going here. So that'll be 7 square root of 7x over 2 times the square root of 49, which is 7, the square root of x squared, which is x. And we're essentially done simplifying that radical. However, how about simplify, divide out those two 7s? And that's going to give us what? That's going to give us 7 and 7. Divide them out, and we will have the following quantity, that is the square root of 7x divided by 2x. And again, observe how our final answer no longer has radicals in the denominator. And again, why would we want to go back and forth between one notation and the other one? Well, again, number one, as I mentioned, with the values of the trigonometric functions, when we evaluate sine, cosine, tangent, etc., for the special angles 45, 60, and 30 degree, that's one reason. Number two, when we go back to section 2.1 and compute the difference quotient of a radical function, we may need this process of rationalizing denominators, which later you will do it in calculus pretty much in week 1 when you compute limits of a functions and take derivatives using the limit process. For those of you who have taken calculus in high school, maybe you know what I'm talking about. All right. However, well, this is not the kind of rationalizing denominators that we're going to do then. Actually, we're going to do a rationalizing of denominators that has 2 terms, not the ones with 2 terms. We do the one with 2 terms, so you get the idea of what we're doing. However, when it comes to the 2 terms, well, we'll see. Okay, so when a denominator has 2 terms, we rationalize the denominator by multiplying numerator and the denominator by the conjugate. Remember we talked about conjugates in the previous topic? So the conjugate, and let me highlight that part, the conjugate of the denominator. All right? And well, how do we obtain the conjugate of the denominator? Well, all we do is just changing a plus sign into a minus sign of the second term, or vice versa. If we have a minus, change it to a plus. All right? And then also recall this little trick right here. Remember how we use that backwards, the difference of squares? Let me write it down. This is backwards difference of squares also known as product of conjugate binomials. And again, when we talk about binomials, they don't necessarily have to be something like x plus 5 or y minus 7. What that is, containing only containing specifically a variable and a number. No, it could be a binomial could be also between a number plus a radical number, that those can be combined. Algebraically, of course. You can use a calculator and get decimals, but that's not the point. All right. Okay, let's do one rationalizing of a denominator for which we have two terms in the denominator. And again, the ones we did before had one single term in the denominator. Notice how many terms in for A, B, and C. All right, let's do one with two. Okay, so our goal is to write this expression 5 divided by the square root of 3 minus 2 in a way that no radicals appear in the denominator. And again, what's the process? Multiply numerator and denominator by the conjugate of the denominator. So, question first. What would be the conjugate of this quantity here? Plus 2. So we would have to change to a plus. Okay. So that'll be the square root of 3 plus 2. And divide by the square root of 3 plus 2. All right? Okay, so this is what we're going to do. Multiply across 5 times the quantity square root of 3 plus 2 divided by the square root of 3 minus 2 times the square root of 3 plus 2. All right, and well, this is the reason why we went back to review how to multiply expressions containing radicals. And well, although again you have an option, you could do the whole foiling if you want, right? However, that's the reason I'm also recalling here the backwards differences of squares. Right? We can do the backwards difference of squares, or if you feel more comfortable doing that FOIL, root of 3 times itself plus root of 3 times 2, and then negative 2 times root of 3, and then negative 2 times positive 2, then that's fine. However you feel comfortable with it, that's fine. All right, and well, that'll give us then, well, what is that? Okay, you know what? I'm not going, let me distribute it. Let me distribute the 5. That's 5 root of 3 plus 5 times 2. So in the numerator, there's no way around. We will have to do the distributive property. Right? And that's 5 times 2, that equals to 10. And in the denominator, well, notice the form. Let me write it with a different color below each factor here. That is A minus B, A plus B. That means, well, this is going to look like A quantity squared minus B quantity squared. All right, so that's going to be then the square root of 3 quantity squared, and then minus the other term B, which in this case is 2 quantity squared. So the numerator will just remain the same, 5 root of 3 plus 10. That's simply 5 root of 3 plus 10. And then divide that by, okay, again, check this out. Check how the radical cancels the square to leave us with a 3. And then minus 2 squared, which equals to 4. And what is this going to be? Okay, 3 minus 4, which is, number 1, 5 root of 3 plus 10. And then divide that by negative 1. And you don't want to leave this result like this. Divide by negative 1. Simply write negative parentheses 5 root of 3 plus 10. Or if you prefer to distribute this negative sign, distribute it. That's going to give us negative 5 root of 3 minus 10. Either one of these two results is acceptable, it's correct. All right? Okay, just above the exercise. Okay, let me do it the other way. In case you don't want to do it with the product of conjugate binomials, that is, by the backwards difference of squares, I'm going to do the following. I'm going to show you how to do it if you prefer to do it this way. So let me write this product, root of 3 minus 2, root of 3 plus 2. All right, I'm gonna do the following. Root of 3 times itself, that's root of 3, and root of 3 times 2, that's so root of 3 times root of 3, and root of 3 times 2, that's 2 root of 3. And then negative 2 root of 3 times negative, and plus negative 2 times 2, that's a negative 2 root of 3, and minus 4. Well, again, do you see the pattern that looks like one we did in the previous page, in the previous handout, in the previous review handout? And let me make some space in here. And this will be root of 3 times itself. That's root of 3 times 3. And then these got canceled, minus 4. And this is root of 9 minus 4, which is 3 minus 4, which equals to negative 1. Do you see how is this same negative 1 we obtained by instead using the product of conjugate binomials or the backwards differences of squares? But I mean, again, if you prefer to do the FOIL method for this, that's fine. I'm okay with that. All right. All right. So.